Hi, my name is Nick, and I'm a R&D engineer here at Heidelberg Instruments in Zurich. And today I'd like to spend roughly around 40 minutes discussing materials for thermal scanning probe lithography and also our direct laser sublimation unit. So there will be time for questions and answers at the end. So ideally, we have around 20 minutes or so. There's about 40 slides for me to get through. But feel free to go ahead and write your questions in the chat or save them for in person at the end of the presentation. Okay, so let's go ahead and let's get started. So I would like to spend a little bit of time and try to show you how we can go from, ideally at the end of this presentation, we can see how you go from solid-like materials like these polyphthalaldeyhde resists that are commercially available, and in combination with our NanoFrazor tool, how we can generate nano and micro structures all within the same film stack. So this is an example of our mix and match lithography capabilities where we can do the nano fabrication with our thermal scanning probe lithography setup, and then complement it with a micron or micro scale fabrication with our DLS module. So just before we get started, I would like to just point out that we are going to be present at several upcoming conferences. So first one that's coming up next week is the ENRS in Paris. So this is the Clean Room User Group meeting. So you'll have a chance to learn about the NanoFrazor and how this is being applied for lithography purposes. So it's a pretty general presentation. If you get a chance, stop by. Next, we'll be represented at the Surface Plasma and Photonics Conference in Houston. There we'll talk about how the thermal scanning probe lithography setup is being used for plasmonic structures specifically. So if you're in the area, we'll be there all week. Unfortunately, don't know exactly when that presentation will be, so you have to come for the whole week. Next is EIPBN in late May and early June. We'll have a booth there, booth number 130 for Heidelberg Instruments. And we also have two presentations, one talking about the fourth beam and how the advances are being made with thermal scanning probe lithography. And then finally, we'll also have a chance to discuss some processing where you can go through an image reversal patterning with the NanoFrazor and ultimately go from nano holes to nano pillars. And last but not least, in mid-June, we also will be at the Biochip conference in Berlin, where you can see how the NanoFrazor and its capabilities are being applied for biological and chemical research. Okay, so just briefly, a little bit of history of the NanoFrazor tool. So you may be familiar with it. If not, we'll just briefly go over it. So in the early 90s, IBM was heavily involved in working with AFM tools and the research for scanning probe microscopy. And really the big leap or the big effort from IBM at the time was in the mid 90s when they wanted to use these cantilevers for making memory devices to ultimately try to compete with CD-ROMs and DVDs and such as a storage media. This was codenamed codenamed in IBM as Millipede. So there's some pretty nice articles online, specifically on Wikipedia, about the history of this project. It's really quite nice. And then ultimately, the goal of using these cantilevers as a storage mechanism for memory was not going to be cost effective, especially when flash memory was coming online and started dominating that time period just due to the scalability of flash, not only vertically but also horizontally with their shrink factors. So in the late 2000s, there was some efforts to look at using these cantilevers for lithography patterning purposes, and some really nice results started coming out in 2010. And ultimately, these results led to several individuals, specifically Philip Paul and Felix Holzner, for incorporating at the time a company called Swiss Litho And this was done in 2012 for making the first commercially available thermal scanning probe lithography setup. And as you go through the years, we were able to apply this to many different applications for grayscale patterning and high resolution 2D to complement your standard conventional lithography techniques such as E-beam and photolithography. And then in roughly 2018, Swiss Litho joined forces with Heidelberg Instruments, and there we started to really couple in the capabilities of Heidelberg Instruments with their laser processing and direct right laser systems. So we were able to incorporate a module called the Direct Laser Sublimation Unit to complement the nano fabrication of t-SPL with DLS. And just briefly looking into the future, we keep on innovating and trying to extend the capabilities of the NanoFrazor technology. So recently we've implemented automated overlays so you can complement seamlessly nano structures or structures of various sizes onto pre-existing features. And ultimately, we'd like to extend this to a multi-tip approach. So going from a single cantilever all the way up to 10 cantilevers working in parallel. So a quick but hopefully thorough enough background on the history of the tool. So now we want to talk about how the thermal scanning probe lithography system works. And ideally, we have three ways that we can manipulate locally a surface through thermal energy. That can be through the removal of a material, can be through the conversion of this material, or we can actually add material in some limited cases through chemical vapor deposition and controlling the environment of the heated tip. But today I'd like to focus on the use of thermal scanning probe lithography with the removal of material. So specifically looking at sublimation and what sort of materials go into allowing for this fabrication technique to work. So with the removal technique, you have many possibilities. You can go through and perform grayscale lithography, which can be used for molding in imprint lithography applications or even for electroplating complex geometries. You can complement the removal technique with a bilayer process where you can perform liftoff or reactive ion etching to pattern transfer into your substrate. And then finally, we can also perform a high resolution etch and liftoff process through a film stack engineering. So within the NanoFrazor technology, there are three key areas that allow us to do really nice lithography. And that starts with the thermal cantilevers. So these cantilevers have four characteristics that are quite important. They have an ultra sharp tip where the radius is less than 5 nanometers or so for interacting with the sample surface. It has an integrated tip heater, so you can locally and precisely control the temperature of the tip. We have an integrated topography sensor that's measuring the heat flow with respect to the surface. So that allows us to have sub-nanometer precision in the z-axis for grayscale lithography. And then finally, having electrostatic actuation on the cantilever allows us to also control the z position very nicely. The second aspect that really starts to unlock the nanofabrication capabilities of t-SPL is using a thermally sensitive resist, specifically this polyphthalaldeyhde or PPA. So this material has quite a few unique characteristics to it, and we'll go into all of these topics in detail in the coming slides. But briefly, PPA is able to be directly sublimated with the hot tip, and this allows for the polymer to go straight from a solid phase into a gas phase locally under the heated tip. It's also an endothermic reaction, this depolymerization, so it is not spreading any heat with respect to this reaction. So that leads to no proximity corrections with respect to the interaction of the tip with the PPA. And then finally, to close out all of the capabilities or the three main pillars of the technology is the closed loop operation. So within the software, we're able to directly pattern the topography in the forward direction, represented by the first step here. And in the second step, we are performing a retrace, or moving in the backward direction to in situ read the topography that was just written on a line-by-line basis. And so what this allows us to do is to actually see what we just patterned and correct for it based on changes to the tip or changes to the surface that we're experiencing, while maintaining a uniform pattern depth or the desired structure that we want to pattern into the PPA. So what do these three pillars of technology afford us? Well, you're able to perform the writing. So heating up this cantilever locally allows you to have sub 10 nanometer resolution capabilities. So writing is really important for us, and this is all done through transfer of the thermal energy from the tip to the substrate or the sample. We have this tip radius of approximately 10 nanometers, and we also have a fast and accurate deflection in the Z direction for patterning and grayscale. We also have this built-in topography sensor. So this allows us to not only perform the lithography in one tool, but we can also perform the characterization in real time, all within the same tool. So this is another critical element or a benefit that's afforded to the NanoFrazor technology. We have this imaging can be performed at high speeds, and this allows for that instant inspection and correction if necessary for complex features. Should also mention that having this built-in reader allows you to perform some markerless overlay. So this allows you to image the surface underneath the sample or underneath your film stack without necessarily having to go to a separate tool to analyze that. And this is a really nice feature that you can find some efforts on in the on our YouTube series as well. Okay. Then moving on to complement our nano fabrication capabilities, we have this direct laser sublimation unit. So this is laser processing with a CW laser operating at 405 nanometer wavelength. And this allows for micrometer resolution, so allowing for faster throughput. If you're patterning contact pads or wiring traces that are not requiring sub 200 nanometer resolution, you can use the DLS to pattern faster, and then also extend the life of your tip that's interacting with the sample. And as we mentioned before in the reading section, we have this unique distance sensor, which allows for plane leveling and autofocus and several other corrections to be adjusted in real time. So we have a lot of data that's being collected on a line-by-line basis. So I hope this video will work. This is just to make sure that we're all on the same page. There were a lot of words before, but this is a 100x slowdown of the actual tool or the mechanism for how the tool operates. So in the forward direction, we're heating into the pixels that are slightly darker with a sub-nanometer grayscale resolution, and then turning off the heater and reading what we just wrote while in contact through our topography sensor on the cantilever. So this allows us to image on the right-hand side of this cartoon. That would be the outputted topography image that we would see and collect in real time, while on the left, this is the inputted pixels that are controlling our depth and temperature. So now to talk about the material removal, you saw that there were a couple different options here for removing material. You can go through this mechanical indentation or going to sublimation directly from a solid to a gas. So just a few definitions to be aligned. The indentation here is representing a thermomechanical indentation. So the polymer or the material here is experiencing a glass transition temperature or a melt point before going through a degradation phenomena. As with sublimation, we're permanently removing the material upon sufficient thermal energy to the sample. So this would be going straight from a solid to a gas. And this is our preferred method of patterning. So just some of the requirements and considerations when looking at materials for removal by sublimation for t-SPL. So we want a direct and permanent removal that is thermally sensitive because we're using our integrated heater to heat up our tip locally. We want it to be a sublimated, as this avoids any sort of liquid phase or intermediate liquid phase. You want to try to avoid this liquid phase due to surface tension and potential material reflow, which could destroy the patterns that you were working hard on. You want a sealing temperature below room temperature. So the sealing temperature for polymeric materials is where equilibrium between the polymer and the monomer is reached. So below that temperature, the polymer will stay as a polymeric form. Above that temperature, the polymer would like to go back to its monomeric state. We would also like to know more about the thermal properties of the polymeric material. So this would be specifically the glass transition temperature when it's going from a glass-like state to a rubbery state. You can imagine that if you have a 10, 20 nanometer structure, and then it starts to reflow, your pattern fidelity could suffer. You also want to avoid any sort of low melting temperature polymers as well. Ideally, these materials should be organic based because that allows for a low thermal activation energy. We want to try to pattern in a reasonable time. So our pixel times are anywhere between 1 and 100 microseconds in a desirable range. So organic materials are preferred for their low activation energies. Ideally, we want to also avoid exothermic reactions due to a proximity effect where the thermal energy can spill over to neighboring areas and disrupt our patterning. We also want the film and structure to be stable with respect to time. So polymeric materials have sufficient molecular weight, so they won't go through any sort of surface diffusivity and move around, or surface mobility. So this is something that we look for. Small molecules may have a tendency to move around on the surface. So some considerations that are desirable, let's say, but not a necessity, is the speed of thermal decomposition. Faster is better here, so it allows you to have a sufficient amount of throughput. You also want to avoid having the redeposition of the material onto your surface or onto the tip. Sorry, this is actually the deposition of the thin film. So you want to be able to make a thin film, ideally spin coating, evaporation that is smooth, and you can apply this to several different surfaces of interest for you. This is what I was just mentioning here. We want to also have a material that is avoiding too much significant contamination or can be removed with a little bit of effort. So avoiding redeposition of the byproducts through the sublimation would be ideal. And then it would also be great if the material that we're using for the removal of a t-SPL imaging resist is compatible with etch processing later, or post-processing. This can be reactive ion etching or lift-off. So we want that to be compatible from a solvent perspective, from a mechanical perspective, so that way we can do our other processing, because oftentimes the work doesn't stop just with the lithography. And ideally, we don't want to be spending too much time in a chemical lab synthesizing material, so we would like it to have commercial availability. So fortunately, over the years, we've been able to show that PPA is a well-deserving primary choice for a thermal resist with t-SPL. We're starting from an ortho-phthalaldeyhde material shown on the right here. This material, this monomer, is able to go through polymerization through several different methods, but primarily we're looking at anionic and cationic reactions. These lead to different molecular architectures or polymeric architectures, being linear or cyclic in nature. It's a thermally sensitive material with a low sealing temperature of about minus 40 degrees Celsius. And you may see that temperature and say, well, operating at room temperature, this material doesn't want to stay as a solid. But due to its metastability, by trapping that chain end with either an end capping agent or with the cyclic architecture in general, it's able to stay a solid at room temperature until you're able to trigger that with a single thermal event of a bond breaking. It has an aromatic functionality, so it's unsaturated, so we have a chance to have a good etch resistance. It has a decomposition temperature at or below any sort of flow state for the polymer, so below the glass transition temperature and the melt temperature. It's a self-amplified decomposition, so that means that as soon as a single bond is broken, it's going to go ahead and unzip and depolymerize back to its monomeric state. And this depolymerization reaction is endothermic, so we don't have to worry about any sort of heat spreading. And this also means that the localized thermal event is self-limiting, which is huge for this for the grayscale patterning that we'll see. It's also a quick decomposing polymer, so we have results showing decomposition at a time scale of 1 microsecond or a little bit higher. And smooth films can be made from sub 10 nanometers up to microns in thickness. So this makes it ideal for multiple levels of processing. And you can use a anisole as your solvent, which is a decent solvent to work with. And then finally, it's commercially available from 2 resist providers, from All Resist in Germany and Polymer Solutions in the United States. So you have a couple options for availability based on where you're located. Okay, so we talked about the materials. So what are the capabilities that have been seen with PPA as a thermal resist? So we have high resolution. So going all the way back to the early 2010s, we were able to see sub 10 nanometer features being patterned, and you were able to have this resolution without any sort of vacuum, and it's a pretty easy technique to get up and running with. So these are some nice structures that were represented to show the resolution capabilities. But then also we can't think of just resolution as a lateral dimension, but also in a vertical dimension. And this is where you have a sub nanometer resolution. This is an example of a sine wave exhibiting less than 1 nanometer of error. And then also a grayscale staircase showing also less than 1 nanometer of variation. So each one of those boxes shown there, the 1 micron or so boxes are representing a individual discrete level in Z in PPA. So mentioning the commercial availability of polyphthalaldeyhde, we have the linear PPA from All Resist. It's known under its trade name of Phoenix 81. Then you have the cyclic PPA from Polymer Solutions, sold under the name of PHA 75. So these are just to give you an idea of the type of architecture that we're working with. You also, these are the homopolymers that we're working with primarily, but you also have a couple commercially available derivatives of polyphthalaldeyhde. And this is in the form of a cyclic copolymer with phthalaldeyhde, but with propanol. And you can get this in a composition of 15% propanol or 25%. And you may ask, well, why do I want to have a comonomer inside this polymer if PPA is so great? Well, it's one thing to show that you can have a customization of the PPA, so it's able to go through copolymerizations, but you can also potentially add some benefit to PPA. So here, propanol has a higher vapor pressure than phthalaldeyhde, and so this may allow for a easier decomposition of the entire polymer structure. Remember, we just need one bond to break, and this polymer will start to depolymerize. So this could ultimately lead to a more efficient removal with thermal energy. However, not all of the advantages come free of charge. Here, the one disadvantage is you would start to look at the etch resistance decreasing due to the aliphatic nature of the monomer of propanol here. So there is no such thing as a free lunch. Other derivatives that are more in the exploratory phase or more in a literature phase is also from the cyclic nature. So we talked about just a propanol that's commercially available, but that pendant group on the comonomer can change with functionality to allow for post-functionalization through click chemistry, through epoxidation to include an epoxy group. Or what's really interesting that I would like to try to show you here is in the bottom right, this silyl group. This material. Oops. Okay, sorry, I don't think I can get my cursor, but in the bottom right there, the silicon-containing monomer is really interesting because this is going to potentially allow us to increase the etch resistance rather than decrease it by incorporating a silicon component that can be oxidized and essentially form an in situ hard mask for better dry etching, plasma etching processing. So that's something to keep an eye out for in the future with us, and there'll be a slide or two on this coming up. So we talked about PPA, homopolymers, copolymers of PPA, but there are other materials that can work as a thermal removal material, primarily through sublimation. So molecular glasses were actually one of the first candidates to be used for thermal as a thermal resist. This is the molecular structure here, and you can form a nice mountain that's beloved in Switzerland of the Matterhorn in a sub what is that, about 5 micron by 5 micron area. So this was a really nice example of the resolution capabilities, and the molecular glass resist was used for this. You can also use other commercially available materials. This is polymethyl methacrylate with a co-monomer of methacrylic acid, also available from all resists. And this is the molecular structure, and this was some work done at ETH by Nolan Lasselin. And these were ultimately going to be used for optical surfaces. So this is an example of the t-SPL being performed with this PMMA co-MA polymer. You also have some other more exotic materials. Polypropylene carbonate was done early on in the late 90s by IBM. You have polyolefin sulfone with another beloved character in Switzerland. And these are just, again, being able to have optionality with the material. Doesn't mean that you need to do this or that these materials have a greater property over PPA. It's just showing the capabilities that perhaps you need a sulfone functionality for your chemistry. You also have another commercially available copolymer, CSAR, a chemically amplified resist, semi-amplified resist based on this polymer architecture. You also have PMMA, which is pretty well known in clean room functionality, that can also undergo sublimation. A really unique one that was also noted by IBM is this polyphthalaldeyhde. Again, showing functionalities that can be incorporated into thermal resist. And then finally, a really nice one showing perylene C being used as a thermal resist. This was a material that was evaporated. So rather than relying on spin coating, you can also see results here from an evaporated thermal resist with 40 nanometer resolution capabilities, all done with the NanoFrazor tool. So just to sum up this section, to say a few words about the thermal resist. PPA is our preferred thermal resist for when working with t-SPL. Both the materials from all resist and polymer solutions are working comparably, so you can't go wrong with either one. There's a lot of processing know-how available internally and also in the literature for using PPA, and it's commercially available. The other thermal resists do exist, and even some are commercially available, but they do have their drawbacks or caveats. So you can have sometimes an increased contamination from the materials that we showed here. There can be a lower film stability with respect to time, and also being aware of the plasma etch resistances. These are just a few points to keep in mind when selecting a resist. And it should be said that evaluating new materials is pretty easy to do. If you're able to make a film, try it. The worst that you can do is lose a cantilever, but you'll gain a lot of knowledge in it. So for me, this is a really nice benefit, a quick and easy way to evaluate new materials. Okay, so at this point, we talked about thermal scanning probe lithography and how to make these nano couple 100 nanometer features. We showed how these features are read with our cantilever with the topography sensor. But now let's dive into the direct laser sublimation and how we can complement these nano features with a micron-sized or larger structures with our DLS module. So within the DLS, this is a laser process. So we're using a focused 405 nanometer CW laser. It's outputting around 110 milliwatts on the sample surface. So we have to be able to operate in that power regime. It's fast. So this is one of the driving forces for integrating the DLS into the NanoFrazor, was to improve throughput while also extending the lifetime of the cantilever. So micron-sized structures can now be patterned with the laser rather than with the tip. Resolution's not bad. We're relying on some photothermal effects, so we can actually get sub-micron resolution, even though our spot size is around 1.2 microns in diameter. And ultimately, this led to a mix and match lithography capability. So this was pretty cool. I thought when I first joined, being able to use the same tool and learn one software and being able to do these various dimensions of lithography. So you're using the same resist, and this allows you to do all of the same post-processing transfer steps and not have to recode or go to a different tool. It's all done within the same tool, the same resist stack. This also allows you to have direct inspection of laser patterns right after with our topography sensor that's integrated in the cantilever. And so you can go from on the left, the layout in our software that has contact pads and electrical traces, ultimately going to, I'm not sure what structure this is at the end, but going to some nano-fabricated, to nano dimensions circuitry. And then on the right, this is the actual optical microscope image of the as patterned features. So in a cartoon, this is how the DLS is operating. So we need to convert that photo energy into a thermal energy. And when we're using just a simple PPA film, this is most likely coming from that conversion of photo energy into thermal energy at that interface of the substrate with your resist. So if we just say a few more words about how the DLS is operating and what you can do to optimize this. These are a few optical parameters shown here for some standard materials that may be used for your substrates and also that we use in our processing. What I would like to point out here is the extinction coefficient at 405 nanometers. So you're looking at materials that are not absorbing a lot of light. So ablation is going to be minimal, if even existent in PPA. So what you can do to try to optimize this is, if your processing allows for it, we have inside our software a writing efficiency calculator that can show you the constructive and destructive interference of your film stack that you're working with. So if your processing would allow for it, in this example here, this is just PPA on silicon. Ideally, you would want to have a film at 61 nanometers in thickness. This would put you at a maximum for writing efficiency. I would say this is underutilized by the community, but it's something that we try to push out more and more, at least the awareness. So if you can, just be mindful of where you are on this graph. So if you're having some issues with DLS processing, or the laser power is requiring more energy or more power than you think, take a look here and see if you're in one of these valleys for writing efficiency. You may be able to just simply adjust your film thickness and achieve better patterning results. So this was just a simple film of PPA on silicon, but we have various film stacks that we're working with here. And ideally, we want to do metallization, we want to do etching, addition, subtraction, these types of processing. So one film stack that's being used heavily is a bilayer liftoff stack. So this is used for depositing thin films of material with a resolution greater than 100 nanometers or so. We also have the same process for liftoff, but with high resolution. This would allow you to perform liftoff for sub-100 nanometer features. We also have a high resolution etch stack where we're changing out that underlayer from a liftoff resist to an organic transfer layer, or an OTL. And this can be used for patterning 100 nanometers or more. And then finally, just to take advantage of our grayscale, we also are looking at film processing where you're using PPA as your etch mask for pattern transfer of grayscale features. And this can be used just for etching, or you can use it for structural sample fabrication by electroplating or for imprint lithography applications. So what I'd like to focus on is the high resolution etch, as we have an example here showing how film stack engineering can be beneficial for resolution and patterning capabilities. So just briefly, this is the high resolution etch processing that we have. It's a 4-layer stack that we're using for patterning into substrates. Here we will spin coat first our organic transfer layer, and then we have an organometallic or a silicon-containing hard mask that will act as our etch mask for patterning into the OTL. On top of that, we have a buffer layer of PMMA. It helps with wettability of the PPA on some of our hard mask materials. And then finally, our thermal resist of PPA. And this is our film stack. As we go through this, we can start to perform reactive ion etching with nitrogen oxygen plasma to break through the PPA and PMMA layer and expose the hard mask for a subsequent processing with CHF3. Then this is opening up the OTL for additional oxygen plasma processing and ultimately exposing our substrate for additional etching to pattern your desired structure. So you may ask, why is this important and why are we talking about? Well, in real world cases, you often have heterogeneous surfaces. And for us, heterogeneous can be anything with different thermal conductivities, different heat capacities, different optical properties, and this can lead to a non-uniform thermal transfer into the PPA film. So you can imagine the difference between silicon and silicon dioxide, or if you're patterning over a metal, these would be extremely different in terms of their thermal conductances. And this can lead to inhomogeneous patterning from your DLS. You can also be patterning on topography, so you could have a film stack, a difference in your film thickness from the spin coating on pre-existing topography. This can be pre-existing materials, nanowires, nanomaterials, 2D flakes, can be existing contact pads that were patterned with a previous lithography step, or just simply from spin coating, you have an edge effect on your sample. This can lead to destructive or constructive interference with the laser wavelength. So ultimately, this can lead to differences in the laser absorption by the PPA and how that thermal energy is transferred from the substrate to the PPA. And this is just one example of a real world case that we've patterned in the past. This is a 2D flake on a pre-existing electrical contact. You have everything here. You have different materials, you have topography. So you have to be mindful of all these surfaces. So how can film engineering help this? Well, we can think back to the optical absorption and potentially exchanging out or using a higher absorbing hard mass material. So our most common one that we use is based on a silicate, silicon dioxide here. But we also are investigating the use of amorphous silicon, which has an extremely high extinction coefficient at 405 nanometers. So what this does in a cartoon is it moves your thermal source or that conversion of photo energy into thermal energy from the substrate and moves it closer to the PPA by having this optical absorber placed just above the OTL layer. So you're bringing your thermal event closer to the PPA, which is necessary for sublimating the thermal resist. So just a few examples here. This is showing the influence of underlayer thickness with respect to the organic hard mask. So this is showing a couple different points that we use, around 82 nanometers. We have almost in the valley of a writing efficiency, but if we increase that to 150, we're able to increase our writing efficiency sufficiently, or significantly is a better word. Now, if we use the amorphous silicon, we see a similar effect as well by adjusting the underlayer that's being used. So if we start to use an 82 nanometer thick PMMA layer versus a 150 nanometer thick PMMA layer. So again, it's just important to know where do you fall on this write-in efficiency curve. So just one quick word here on how to measure the influence of the film stack. So we look at increasing power and speed on each respective axis here. So we'll see some topography images collected from the t-SPL tool, and this is how the nomenclature is working. In the y-axis, we're increasing power. X-axis, we're increasing speed. So first, we look at our silicate hard mask, and this is with a film stack shown here. So most important part is that it's 82 nanometer thick PMMA underlayer. And we see that we start to experience some thermal damage around the higher powers, around 60 milliwatts, and at the slower speed. So you're essentially having increased energy for that square. Now, if we just simply increase the PMMA thickness to 150 nanometers, where we're at a higher point or at a maximum for the writing efficiency, we are seeing that we're much more sensitive to the laser power. In fact, there's not much of an overlap between the two film stacks here. And so this is an exaggerated example, but you can now think about this spin coating on topography where you have thickness variations on top of your structure or in between your features. So now if we exchange out that silicate hard mask with an amorphous silicon hard mask, similar film stack, but now we're just replacing the amorphous silicon. What I want to pay attention here is the y-axis and the power values. This is for 82 nanometer thick PMMA. Now, if we go to 150 nanometer PMMA thickness, we have a significant overlap between the two film thicknesses. So this would allow for a greater accommodation of film thickness variation across your wafer or on the structure of interest that you're patterning. And then finally, looking at the influence of the substrate. So this is the use of silicon with amorphous silicon hard mask. And again, pay attention to the power values shown here. Now we change over to a glass substrate, and we're still within the same regime of power and speed where we're able to write sufficiently. If we go to an SOI-like wafer, we also have a similar process window. It's not large, but at least it gives you a chance to process all of these materials on the same surface with this film stack. Then just a couple words about high resolution capabilities. So we go back to the 82 nanometer thick PMMA layer just to show how much thermal energy is being deposited into the film stack. This is the topography image collected after the DLS processing. And if we take a look at the profile of one line here, we see this bump in the middle of our structure, this right around 1 micron in X. So if we zoom in into one of these lines, we can see that there's a thermal stress that's being built up in the underlayer, and it's relieving that stress through a wrinkling effect. And this is, perhaps it's okay for your processing, perhaps it's undesirable. For me, I don't like it. So this is where you can think about, I don't have to use just PMMA as my organic transfer layer, but I could also use something that is more thermally stable or more in the thermal regime of interest for this type of film stack. One such material is a highly carbon enriched underlayer from JSR, that's HM8006. And if we switch that out with this film stack from previously, perform a similar patterning, we see that we have a very nice and clean uniform structure such that we are exposing our hard mask for further processing without any sort of detrimental stress effects coming from the underlayer. If we take that same film stack and just start to push the resolution capabilities, we start with a couple hundred nanojoules per pixel, and we start decreasing that, we can see a resolution of roughly 300 nanometers or so. If we want to look at a true pixel, single individual pixel exposure with the DLS unit, we are able, with this film stack, to get around a 600 nanometer in diameter via. So with that, I would like to just summarize some of the DLS materials and what I hope you can take away from that section. If you are using the tool and you have access to the tool, please make use of the laser efficiency calculator in the software. If anything, it just gives you an idea of where you're operating and how easy or difficult the DLS processing should be. And if it's possible, modify your film thicknesses to a maximum in terms of write-in efficiency. This could allow for a larger process window and greater flexibility when you're patterning. Most organic materials are very poor absorbers in this wavelength range that were of interest. That's 375 to 405 nanometer, which also includes PPA. So the sublimation of PPA is most likely a combination of that conversion of photo or light energy into a thermal energy, and to a lesser extent, actual ablation or absorption from the PPA. Be aware of the optical absorption of your film stack. Most often, this could be coming from the substrate. So just keep in mind what your N and K values are of the substrate of interest for you. And if possible, you can think about ways to move that optical absorber closer to the PPA for a more efficient removal or sublimation of PPA. And last but not least, be mindful of the thermal properties of your underlayer. This would be glass transition temperatures and things of that nature. So not as critical as the other points, but something just to be aware of. Okay, so for the fun part, what are we doing now and where are we going? So right now, we are actively looking at complementing PPA or other resists that are positive tone thermal resist with negative tone resist. So can we apply a selective thermal treatment in the form of a selective post-apply bake, a selective post-exposure bake, a selective cross-linking phenomena, and use this for the inverse tone of PPA? Right now, we have several candidates that are showing promise, and I would say the community should be on the lookout for this type of work coming out in the near future, or at least an update from us in the near future at conferences and presentations. We are actively investigating materials for inert environment processing. So the nice thing about the NanoFrazor technology is that it can be integrated into a glove box condition without the presence of oxygen or humidity. But when it comes to the PPA removal, PPA is sensitive to acidic environments, or even in the presence of water. This catalytic event helps to remove or degrade PPA. So we have to see, is there an advantage to the architecture or copolymerization of these materials? Can we look at potentially increasing additives, either moisture absorbers or oxidizers? And then finally, working with our partners at All Resist and Polymer Solutions, could we modify the PPA directly such that it can undergo degradation in a zero humidity, zero environment, oxygen environment? So these are all efforts that are ongoing right now. We also are looking at increasing the etch resistance of these thermal resist. This is done by incorporating a silicon-containing comonomer into the PPA, both for linear and for cyclical architectures. So this requires an additional post-processing step, either with oxygen environment or potentially other types of etching conditions where you can form that hard mask in situ. So this is also an ongoing material effort for us. And then the one that I get most excited about, especially from a scientific perspective, is can we thermally trigger and instantly generate functionality of materials with the t-SPL tool or DLS module? Could we directly pattern electrically conductive structures in the form of metallic nanoparticles, or could we even start to selectively make high refractive index features directly without requiring post-processing? I know this is really out there, but this is the type of mindset that we have when it comes to materials. Then just a few take-home points as I stop here in a minute or so. I hope you can take away from this that PPA is our preferred material. Both linear and cyclic architectures are working extremely well. The material options are readily plentiful, but be careful because they do require work. However, I would say that the tools are there for this material evaluation if you have the time and energy. With DLS, be mindful of the optical properties. So keep the extinction coefficient and the refractive index in mind when you're making your film stack or designing your experiments. And material research here at Heidelberg Instruments is not only going on as in terms of ease and simplification of processing and generating new functionalities, but we're also seeing how chemistry and materials can start to improve endurance for thermal scanning probe lithography, as well as tip contamination. The longer that we can pattern, the better, in our opinion. And I think material will play a critical role there. And last but not least, have fun with this, because it is fun. So if you have some interest, we're always happy to discuss new challenges, new application, new materials. Reach out to us. I didn't put our support email here, so maybe Felix, if you can put the support email inside the chat, that would be great. Sorry about that. Or come back for the second session in the afternoon and it'll be there. So with that, I will stop here and take questions.